Lecture 7.3, Diagonalizing Basis. It is useful to transform a system's state vector x into a special basis that diagonalizes, that is, leaves non-zero components along only the diagonal, the system's A matrix. For systems with n distinct eigenvalues, to which we will limit ourselves in this discussion, this is always possible. So if you have repeated eigenvalues, some weird stuff happens. You can't totally diagonalize it, but there's this, in this footnote, it describes an appendix lecture that discusses that possibility. But that's not going to be, we're not going to have that show up in problems in this class. It's beyond the scope. So in diagonalized form, it will be relatively easy to solve for the state transition matrix phi, which is our main motivation for doing this transformation in the first place. So changing basis in the state equation. As with all basis transformations, the basis transformation we seek can be written as being take a vector, operate on it by a matrix, get out a new vector. Where P is the transformation matrix, X is a representation of the state vector in the original basis, and X prime is a representation of the state vector in the new basis. So this other equation is just the other side. Prime here, prime does not mean derivative. Prime. In this context, I don't use prime for derivative in this class at all. So you're never going to see that. Prime here just means it's a new x in a new basis. Now, caveat, we're breaking math again because a vector is an immutable object, geometric object. And when we change basis for that vector, we don't actually change the vector. So if this was our x vector, when you changed basis to the new coordinates or to the new basis, you're just remapping what your system is. So maybe this was my original basis was based on a unit vector here and a unit vector here, and my new basis is based on a unit vector here and a unit vector there. Still describes the same immutable vector just in a new basis. I don't know why we are really bad at teaching this stuff without abusing the hell out of the concept of what a vector is, but we are bad at it. So just try to keep that in mind, that when you change basis for your vector, the vector is really the same vector, it's just that you changed your representation of it. So that's something to keep in mind on this. Great, so basis transformation is what we're doing. These are the formulas that go back and forth. So to go from x prime to x, you have this transformation. To go from x to x prime, you have this transformation. Great. Substituting this transformation into the standard linear state model equations yields the model. So x prime dot means the new basis x, so the primed basis x, time derivative of it is the dot. This was just a simple plug and chug. I plugged it in and then solved for what x prime dot was. And we get this nice similarity transform. It's called P inverse AP, which is our new A matrix. We'll call it A prime. And it multiplies the new state vector x. And we have this new B prime, which is P inverse times B, and a new C prime, and a new Optimus. No, just kidding. D prime. And that's our new primed basis state model, which is totally fine. So if you start off with a state model in your original basis, you want to transform it to the new basis, all you have to do is take that basis transformation matrix P, plug it in, find your new A, B, C, and D matrices. They're primed versions. Great. So that's generally true. And now let's look at two definitions that are going to also go into this derivation. So let a state equation have matrix A. Let's see, where am I in my notes? There we go. Let a state equation have matrix A with n distinct eigenvalues, lambda I, and eigenvectors mi. Let the eigenvalue matrix be defined as, so we're going to use capital lambda here. Lambda equals, it's just going to be all of the eigenvalues along the diagonal. So lambda 1, lambda 2, down to lambda n, and we're going to have zeros everywhere else in the matrix. That's the eigenvalue matrix. And when you use a certain syntax in MATLAB, when you find the eigenvectors using the eigenvalues and eigenvectors using the eig function, it'll return this matrix to you. It knows and loves us and wants us to succeed. MATLAB. That should be their slogan, I think. Unfortunately, I'm not being paid by MATLAB to say that. But I should be, right? I feel like I should be. Yeah. Okay. Furthermore, it's another definition. Let the modal matrix M be defined as the matrix you get when you put the eigenvectors in a row. So they're all column vectors. That's what this notation with these vertical bars is telling us. They're column vectors that comprise each column of the modal matrix M. Sometimes we also call the modal matrix the eigenvector matrix because it's just composed of eigenvectors. But modal matrix is the more common term. So we're going to use lambda, the eigenvalue matrix, and we're going to use the M, the eigenvector matrix, or the modal matrix, in the diagonalization of the state equation. Okay, so let's do that.
How big is the modal matrix?
The modal matrix is going to be, so there are n of these eigenvectors, and each of them is an n by 1 vector, so it's going to be an n by n, so n by n matrix. As is lambda, this is also an n by n matrix.
Is there zeros at the tail of the ends? The other matrix, the modal matrix?
Oh, so these, this is full of, so the M1 vector is like a column vector with n values in it. So I would say it would be like M11, M21,
Filled with M.
yeah, etc. all the way down. And then the next one over is going to be the M12, which comes from the M2 vector, M22, etc. So it's filled with the eigenvectors. So diagonalizing the state equation. So let the modal matrix M be the transformation matrix for our state model. So like for no apparent reason, we're going to do this, right? We're going to say, okay, let's say our transformation matrix, instead of just being some P, some random matrix that we come up with, let's make it be the modal matrix. See what happens. Good things happen. That's the secret, right? So here we go. So this is our transformation from x to x prime. The state equation becomes this, which is just the same equation we had before, but with p in it, and it gives us our new state equation. Great. So the eigenproblem implies the following identity, which we can see as being a bunch of eigenproblems all concatenated together. So let's write M1, M2, dot, 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 down to Mn. And we have, if you're, keeping score at home, we have just written the modal matrix there. But that we're supposed to just sort of discover as we go. M1, M2. I'm not using the vertical bar notation here, but this is the same that we saw, same matrix we saw before, times lambda. So this is actually, if you look at this as a bunch of individual eigenproblems, this kind of makes sense, because this first AM1 is going to be equal on the other side to M1 lambda 1. And then AM2 is going to be equal to M2 lambda 2. So it's effectively the same. It's the eigenproblem, but just all of them in a big row together, mashed up. At least that's one way to think of it. So what we have then is AM equals M lambda. And let's see if we can get this term to pop up here. So that's my goal. I want to see this term pop up and see what it's equal to. So M inverse AM means I need to left multiply by M inverse AM equals M inverse M lambda, which if I switch left and right sides of the equation actually gives me a solution for, well, I won't switch it. I'll just say those cancel, and this is just equal to lambda. So M inverse AM, which is our new A matrix, right, is just equal to the eigenvalue matrix, which is pretty cool. Okay? So A prime, the new A matrix, is just lambda. Recall that lambda is diagonal, therefore we have diagonalized the state space model. So the new A matrix, the A prime matrix, is diagonal. It's just the eigenvalues along the diagonal. Great. In full form, the diagonalized model has A prime being lambda, B prime, C prime being these transformations of the original B and C matrices, and then the D matrix is the same as it was in the original model. Okay, so we've learned how to diagonalize our state model, which is useful. But the big payoff is actually this next bit. Okay, this is the real motivation for doing it. I mean, having a diagonalized system is kind of interesting, but we're going to see some of the payoff here in a sec. So recall our definition of the state transition matrix as being e to the AT, right? The matrix exponential of AT. Directly applying this to the diagonalized system of equation 718, we have that it's the matrix exponential of lambda t. So A prime is lambda. So our phi prime, our state transition matrix in the primed basis, is e to the lambda t. And we're going to use this diagonal property of the state transition matrix that we introduced in the preceding lecture, which told us that, or I know it was 2 lectures ago, which told us that if you have a diagonal matrix as your argument for the matrix exponential, then you can just put the exponentials, the scalar exponentials, in the diagonal and raise the diagonal of the original matrix to each power. So in other words, if you take the matrix exponential of a diagonal matrix, you get a diagonal matrix of exponentials. What?
Say it fast 3 times.
Yeah, that was fun.
Can you just say it once slowly?
Yes, please.
Again? Yeah, okay, I'll try. Let's see if I can succeed. So the matrix exponential of a diagonal matrix is a diagonal matrix of exponentials. I did it. Yes, thank you. Thank you. I think that I said it properly also, which is a plus. Yeah,
what is the state transition matrix? One more time.
Yeah, so it plays a large role in the solution that we derived for the state equation. So remember, we derived a solution for the state equation in, I think, lecture 7.1 it was. And it included this matrix exponential, and we defined a specific matrix exponential to be the state transition matrix. What we said was phi of t, the state transition matrix, for a system with an A matrix A, so with a given A matrix, is exp of AT. That was our definition. And this is also equal to e to the AT. Those are two equivalent ways of writing this matrix exponential. You know that it's not a scalar exponential by the fact that you have a matrix in the exponent. That's how you know that it's a matrix exponential. So we defined it, but what we used is a series definition. We used this definition that, let's see if I can remember this, the sum from k equals 0 to infinity. I can't remember if k is 0 or 1. 1 over k factorial times the argument, which I didn't give, the argument matrix here. This is like big Z, raised to the kth power. And what this was defined as being E raised to the Z matrix. E to the Z matrix is this by definition. That definition you're going to use in a couple homework problems. Go back to the definition to find what the matrix exponential is. But I said back then that's not the best way to compute the matrix exponential. The best way to compute it is to actually find the diagonal one. Once you've diagonalized your system, it's trivial to find the state transition matrix. And we're going to use that as our method. Okay. But what I'm going to do now is I'm going to take us a little bit further. So first what we're going to do is we're going to look at this diagonalized system, its free response for just a moment, just to get a sense of what we've done with this diagonalized system. So recall that the free response solution to the state equation is given by the initial condition and state transition matrix. So this was the free response. So remember, the free response was just the state transition matrix times the initial condition. So in the primed coordinates, our free response is the primed coordinate state transition matrix times the primed coordinate initial conditions. And what we've done is completely decoupled each initial condition from the other exponentials that decay. So all of our eigenvalues that govern these decaying exponentials are going to be decoupled from each other in the case of n distinct eigenvalues, at least. So that's kind of interesting. It's like we've sort of combed our system straight so that all of everything's decoupled from each other. And that gives us a better sense of what these modes are. We're calling them modes. These eigenvalues are defining these eigenvectors, or think of it as the other way around, for our system. And what is the significance of them? They're kind of these things that are decoupled from each other. The other things can be thought of as being comprised of. And that's what you're going to think of in vibration theory a lot, is like, what are these different modes that my system has? And if we excite this mode, what happens? If we excite that mode, what happens? How do we avoid exciting this mode that is potentially dangerous? So you're going to learn all about modes in vibrations. But you're going to see all of the theory here that you need in order to construct that. Also, if you're going to work in the primed coordinates, you need to transform your initial conditions, because presumably they came in the original basis when your problem was defined. So you have to transform them in the same transformation as every other x variable that you have to get into a primed basis, you need to go through this transformation. So we have completely decoupled the state's free response, one of the remarkable qualities of the diagonalized system. At this point, one could simply solve the diagonalized system for x prime, then convert the solution to the original basis using this basis transformation. So you could, when you see a problem and you're like, I want to solve for what the state response is of the system, you could convert it into the primed basis, solve it because the state transition matrix is easy to find in the primed basis, and then just convert your solution using this transformation to get back to x at the end. That's totally a valid way to go. Typically, we choose another route, even though it's pretty much equivalent. So there's really no reason one's better than the other. I would just say it's just more common to do. So sometimes we might prefer to transform the diagonalized basis state transition matrix into the original basis and use the phi in the original basis. So what the following is a derivation of that transformation. What we want to know is how to transform phi prime into phi, okay? So that we can just use the state transition matrix in the unprimed coordinates, in the original coordinates. So that's what we need to derive. And I'm going to do that by beginning with the free response solution in the diagonalized basis and transforming the equation into the original basis, which gives us an expression for the original state transition matrix as follows. So this is like a fun little derivation. So we start off with the free response in the primed coordinates. So by definition, this is phi prime of t, x prime of 0. So these are the primed initial conditions. So everything's primed. This is the free response in the primed coordinates. Great. Now let's transform each of these x primes into the unprimed x. So every time we go from an x primed to an unprimed one, we can use the transformation m inverse x x free of t. So what I've just said there is that x free prime of t is equal to m inverse x free of t, which was the original basis transformation equation. So that's all I did on the left-hand side. I have to do it to the, or I can, and I'm choosing to do it to the other one too. So phi prime of t, I can transform the initial conditions using that same transformation. So m inverse x, so our original initial conditions in the unprimed coordinates, show up there. And now if I solve for x free on this left-hand side, I get what the free response is in the unprimed coordinates, but I have the phi prime in there still. So now we're getting somewhere. So now if I left multiply by m, we get x free of t equal to left multiplying by m. So left multiplying by m here canceled this m. So m and then phi prime of t, m inverse x of 0. So this is the free response in the unprimed basis, and this is the unprimed initial condition. So therefore, by the form of this, the definition of our free response, or our derived form of our free response, this is the state transition matrix of the unprimed system in the unprimed basis. So this last expression is just the free response solution in the original basis, so we can identify that phi is just this, m phi prime m inverse. This is a powerful result because we can actually use this as our preferred method for deriving the state transition matrix for a given system. The eigenvalues give us what phi prime is. Phi prime is just this. So all we need to do is find the eigenvalues of the system, and we have phi prime, bang, by equation 719b, and then all we need then are the eigenvectors of the system, and they'll give us this transformation to get to phi. And that's what we're going to prefer. And you're going to see why, because when you do the homework, you're going to find that it's very tedious to do this from the definition, to find phi from the definition, given before that series definition. This one I would describe as not gonna have a good time. If there are any South Park fans out there, you might recognize that reference. South Park fans?
Yeah, I don't get that
Wow, that's so crazy. It's weird because South Park's still running, so somebody's still watching it. It must be people my age that are watching it.
one. Yeah, I've watched it in a different language.
Really?
They've changed everything.
Interesting. It's a filthy, dirty show. It's filthy.
wasn't.
It wasn't in the other language.
It was a good show.
Interesting. That would be so interesting to watch. Like the English translation of the other translation. That'd be great. Okay, so yeah, good. So this is going to be the preferred way that we do it, and so what our system solution is going to give us is it all depended on the state transition matrix. That's the only thing you needed to find the solution to the state equation. And it was going to be hard to find that state transition matrix before, but now all you need to know are the eigenvalues and the eigenvectors, and you've got your solution. So that's pretty sweet. And that's our preferred way to do the analytic solution to the state equations. So we'll do an example on Monday. Okay? I thought about doing a weekend example, but I don't think people like this.